And that's where you all come in. We'd like to share our experiences with you, our learnings, so that we can make Kubernetes better together. I'm Joe Betz. I'm the lead engineer for etcd at Google. I'm also a maintainer of the etcd project and a contributor to the Kubernetes project. Joining me today is Wenjia Zhang, who is also a contributor to both Kubernetes and etcd. We'll go over a brief recap of the Kubernetes control plane, remind you of some of the components that are in it. We'll then walk through some general diagnosing strategies that you can use with the Kubernetes control plane. And then we'll get to the heart of our talk, where we'll go through real-world examples of an actual issues with Kubernetes, and we'll pair each of those issues with a key concept from Kubernetes that you can use to inform your diagnostics work. We'll then close it up with some guidance on how you can keep your Kubernetes healthy, your clusters healthy proactively. So let's just briefly recap the control plane. The Kubernetes control plane is inspired from the shape of a ship's helm. Kubernetes literally means helmsman, and a helm has a hub in the center and spokes that go out in every direction from it. The Kubernetes control plane has a central component and then a series of components that interact with it to do work. That central component is called the Kube API server, and it provides a RESTful interface that the other components communicate with to determine the state of the cluster, apply their business logic, and then apply the changes they want to make to the cluster back to it. Nestled beneath the API server is a distributed key value store called etcd. There's a lot I could say about this, but for now we'll just remember that this is the persistent storage system for the control plane. Let's go around some of the spokes. The first is the controller manager. This is a bundle of controllers that run in a single process. Some of those controllers you might be familiar with because they map directly to a concept in Kubernetes. For example, the service controller is responsible for the business logic of service resources, and so you can kind of inform your understanding of what it does based on that. Some of the controllers provide an auxiliary function. For example, the garbage collection controller is responsible for cleaning up resources that aren't needed by the system anymore based on policies. Okay, we also have the cloud controller manager. This is responsible for integrating with the various cloud providers that Kubernetes supports. It's the primary integration point for them, and it's the interface that hides the differences of the cloud providers from Kubernetes so you get a uniform experience. Of course, Kubernetes has a scheduler. I like to think of the scheduler at a very high level as being primarily responsible for mapping pods onto nodes. It's the responsibility of the other components to get the pods created so that the scheduler can then schedule them. Most Kubernetes clusters have some extensions installed. Maybe they're installed as part of the Kubernetes distro you use with your cloud provider. Maybe they're something you've installed custom onto your cluster. I'd encourage you to take some time to understand the extensions that exist on your cluster when you're diagnosing it. That can be very helpful in making sense of problems when they occur. Just really briefly, whenever I talk to people about Kubernetes, the first thing I remind them is don't panic when you're diagnosing problems. This is important because, first of all, panicking doesn't help, and also Kubernetes is designed so that the control plane is not a single point of failure. All the nodes will continue to run the pods that have been scheduled on them until the control plane recovers, so you can continue to run your mission-critical software while you recover the control plane. A common question I get when people ask me about how to diagnose control plane problems is there some kind of logic or mapping that I can apply to the various problems that I might encounter and the locations in the system where that issue is happening? And surprisingly, sometimes the answer is yes. So for example, in the Kubernetes API server, if you get a 500 series response from that in HTTP, that literally means the API server is telling you that it knows it has an internal server error, and it will give you a message telling you some more details, and you can go directly to that component and start inspecting it. But in many cases, a single symptom can map to multiple causes. And for these, even if you've seen the symptom before and remember what happened last time, I'd encourage you to work stepwise through the process because it could be a different issue this time. This is the template we'll use in the examples we're about to show. We'll start with some symptoms, and then we'll work our way all the way down to a root cause, and then we'll take it one step further and look at mitigations and things that you could do immediately to get your cluster working again. So let's walk through some examples. We'll start with the first one. Our key concept here is that all component and interaction in Kubernetes is observable. And what that means is that the Kube API server, the hub of that helm, performs no business logic of its own. And the components that communicate with it, everything from the master components to the extensions to the nodes themselves and even you, the user, must interact only with the Kube API server and cannot directly communicate with each other. As a result, all communication between all those components is going through this central point, and you can inspect all of that interaction. You can do that quite simply just with the kubectl command line tool. For example, if you use a git, you'll see a pod, and if you use a describe, you'll see that same pod with more detail. But it's important to know that describe doesn't show all the details of a pod. It shows the most essential information. If you want everything, you really need to drop down to outputting the resource in either YAML or JSON, and then you will get each and every field that exists in that resource. Sometimes the change will only be visible here. Those commands will give you a snapshot of a resource at a point in time, but if you actually want to see what's changing over time, sometimes you need to watch things. There's a flag to do that, and here we see an example of where we're watching a single pod, or all pods actually, and one of those pods has been created and then deleted afterwards. And you see each and every state transition it goes through in your terminal as it progresses. If you needed to, you could use that same command with output YAML, and you would literally get an entire copy of that resource every time it changed in any way. So this gives you extensive details of what's happening. Let's use that to look at an actual problem. Here we've got a pod that has been stuck in a terminating state. Pods in Kubernetes should only take a couple minutes or a couple seconds to terminate at most, but this one's been stuck in this state for over 35 minutes. There's a couple ways that you could find the next thing. You could search the web and ask, what are the common causes of pods getting stuck in terminating state? And you'll get a bunch of hits back, and some of them will talk about finalizers. Or you could just go directly and look at the resource and see that there's a finalizer, like the one shown here on it. The next step might be to learn a little bit more about what finalizers do, and what you'll learn is that controllers create finalizers and then are responsible for removing them when they're done with whatever work they needed to do. And it's only after all the finalizers are removed that a pod is removed. So that's clearly our problem. We've got a pod that's not being removed because there's a finalizer still on it. So why is there a finalizer, and what controller was responsible for it? Well, if you dig a little further, you might find that the finalizer includes the name of the component, so you can use that, do some searches, ask your colleagues, and find that this is a third-party component that was installed in your cluster. And there's also a known issue with it where sometimes, under certain conditions, it doesn't remove its finalizers, and that's been fixed in a later release. So you could then now start to actually sort out the problem. If you needed an immediate fix, you could literally edit the YAML and remove the finalizer, but that's a little risky because now you're doing a hand edit, maybe a production system. So another alternative would be to upgrade that controller to the version that says it fixes the problem and see if that cleans up the terminated pods. Let's look at one more example. This one is based on the concept that all state is persisted in etcd. This is really useful to know because if your cluster becomes unresponsive to the point where you can't interact with it through the API, you can still go down and look at the data. etcd stores a history of data. It doesn't just store the latest version of objects. When you update them, it keeps track of history. It uses this to provide a watch mechanism so that you can see changes over time. Because of this, you could imagine, well, if we keep updating objects, the storage space will grow indefinitely over time. So etcd provides a way to compact that old history away. With Kubernetes, that's done from the Kube API server using the flag shown here. And by default, it compacts every 5 minutes. So every 5 minutes, everything older than 5 minutes is deleted, which means right before compaction occurs, you can have up to 10 minutes of historical data. You can use that to do some back-of-the-envelope calculations on how much space might be used, where the revisions and the compaction window are used for that last factor. And this becomes important because etcd is designed to store critical state for a cluster, and most Kubernetes clusters only need a couple hundred megs of that type of data. etcd, by default, limits you to 4 gigabytes. You can change that setting, but that's the default. And if you hit it, you'll trigger an alarm, and it will stop allowing writes. So let's look at an issue. Here we've got a cluster that's become unresponsive, and we look at the logs, we see this etcd data space exceeded error. Some of you may have seen this one before. My favorite tool to diagnose these is called Augur. It's a tool that we've written in open source. It allows you to take an etcd data file, even if the cluster isn't running, and analyze it. You can look at specific objects and see them in YAML, even if they were written in protobuf. You can examine the whole key space in aggregate as well. Here I'm going to ask for 3 main fields. I'm going to ask for the total size of each object, including all historical revisions. I'm going to ask for the current revision size, and I'm going to ask for the number of revisions for that object. And then I'm going to sort it by the biggest ones first. And what I get back, and I just showed a sample here, is about 5,000 of these minion objects, which are about 15 kilobytes each. Well, that space adds up, especially considering you've got 120 revisions of each of them. And so you could do a back of the envelope calculation and sort out that, well, if all of them took up that much space, we'd be well over 8 gigabytes of storage space. Clearly we're not, because we hit the 4 gigabyte limit. So what happened? Well, in this case, our cluster had just been resized from about 1,000 nodes to about 5,000 nodes. And when it was sizing up, that's when it failed. Another question you might ask is, well, why is it being updated 12 times a minute? Well, if you do some research, and this is a little advanced, you might find that all the nodes in Kubernetes do a heartbeat update to the Kube API server every 5 seconds. And so that's where those writes are coming from. You can calculate all this together and sort out what's going on. The last remaining bit is why is each node object 15 kilobytes. You might examine that by hand, and what you'll see is a large list of Docker image names. It takes up almost all the space, and it's in every node, and it's the same list. Well, this is a preloaded image list that you can put in Kubernetes, and it allows each node to load Docker images before pods are scheduled that need those nodes. And that means that when pods are started, it's very efficient. But this is taking up a bunch of space. There's 3 things you could do to resolve these problems. You could reduce the compaction interval. That'll cut your storage space in half, because you'll be storing half so much history. You could increase the etcd storage size. There's no reason it has to stay at 4 gigs. You could go to 8 or 16. Or you could reduce that preload image list, and you'd be back to a reasonable size. I will hand it off to Wenjia for the next examples.
Thank you, Joe. All right, so the next key concept that we're going to introduce here is that all the components are containers in the master kubelet. So we're going to start by reviewing some basic Kubernetes concept. What is Kubernetes Pod? Kubernetes Pod is a group of containers which share the same pod spec to make sure that all the container or containers on one pod all function the same way. And then we have this kubelet, which is agent on the node that makes sure all the containers are running properly. So the pod spec is applied by this kubelet in the format of YAML or JSON file. And we know that's the case for any of your workload node. And guess what? Master VM is nothing but another node using this kubelet to run the pod. So it's like the Inception movie, right? The 盗梦空间, 是吧? You're dreaming a dream in your dream. So the magic is really just played by this different manifests for different components. Like if you are applying an etcd YAML to a pod, that pod is turning to an etcd, and so on and so forth. That way, you turned a vanilla node into a master node with all the different components running on it. And that master node is the control plane for your Kubernetes cluster. So since the master components themselves are managed using pod, it gets all the benefit out of it. For example, the master kubelet could use the liveness and readiness probe to check the healthiness of each component. And if any of them is crashed or unresponsive, the master kubelet can restart it. So the control plane is like any of your workload node. It's predictable, repeatable, and immutable. And when it comes down to diagnosing a control plane issue, it becomes very handy too. And now with that concept in mind, before we get into any of the real-world issues, I want to give you a list of nice tools that you can use for sanity check. The first one is kubectl get nodes. It's really just used to check if all expected nodes are present and in ready status. And you can see there, master is just another node, right? From that point on, you'd better have access to your master VM. Once you're on your master, you can use Docker PS to check the process status of your Docker containers, which are the master components. And you can see we have SCD, scheduler, API server, controller manager. If some of them are not there, your control plane is probably in trouble. And then we have this kubectl get component statuses. You can check the health C and metrics of any of the component port. We're going to use some of them in our real-world issues. So in this section, I'm going to cover 3 different examples of 3 different control plane components. For the first one, let's try using this kubectl get component statuses. And apparently, among all the different components, controller manager is not happy. And if you check the health Z to the controller manager port, it's going to tell you the same thing, cannot be connected. And you know what? We can actually check the controller manager log. If you don't already know that, each component have their own log. And turned out that the controller manager crashed because there is error starting this resource quota controller. And you keep reading. There is something suspicious. This blah blah thing might have some issue with it. You probably want to either remove this or fix whatever problem with it. But in this case, what worries me even more is that the controller manager should not fail this easily with any transient error, right? 就不能为了一棵树放弃整片森林，对不对? Our control plane, the controller manager should have a better way to handle errors like this. So, what we're going to do, the easiest way would be to check online and see if there is any known issues. And given that so many people are using Kubernetes, whatever problem that you are facing is probably already discovered by somebody else or even fixed, which is exactly what we see here. So there is open Kubernetes issues, and there is fix on it. And once you get the root cause, the solution is very easy. Short term, you want to remove or fix this service on the node side. And long term, you do want to upgrade your control plane to whatever version that have that fix. Now, in this example, you can see this kubectl get component status is very powerful. You can feel like you got the ultimate weapon to diagnose any control plane issues. Ta-da! Sometimes it's not working. That's not good. Well, what does that mean? If I remember correctly, Joe just mentioned that everything is talking to API server. And guess who is kubectl talking to? API server. So if your kubectl is not working, sometimes it means your API server is not working. And 8080 is actually the default port of the API server. And we check the API server log. What do we see? It panicked. That's not good. Do we panic? Don't panic. Remember, Joe said don't panic. And we're software engineers. We can read stack trace. And turned out there's something wrong with this aggregator controller open API. Some of you might already know what that is. Some of you might not. I don't care. It doesn't matter. You can always check online. And apparently, this is a no issue again. And there is issue opened in kube open API repo. There is fix with it, and there is Kubernetes fix that pick up that fix in open API. With this example, if I remember correctly, everything happened like within 2-3 days. And I did a little survey before this speak. I know there are a lot of contributors. So I want to say that open source Kubernetes communities rocks. Let's give a round of applause to all the contributors. Thank you, thank you. We did a good job. Let's continue doing that. we still have to fix this issue. And it's easy. Just upgrade your control plane to the next version that have this fix. For these two examples, when you have a control plane is not working right, for both example, you have a broken components. What if you, from this two fix, you can see that we tried really hard to make sure our control plane do not fail because of transient error. How about if we have a funky control plane, but everything looks fine? We do not have an unhealthy component. We do not have a broken component. How do we know something went wrong? Which part went wrong? This is when a good monitoring alerting system is very necessary. And remember, Joe said that HTTP 500 error is a very good indicator. They're saying that API server is wrong. In this case, in our system, we have a monitor counting how many 500 errors we got from the API server log. And if it's too many, we got alerted. Now we can look at the API server log. And turn out it failed to list this HPA under this version extensions v1 beta 1. What do we do next? We got the keyword. We can search online. And in this case, instead of finding the exactly issue that we see, we find why we had that issue. Turn out from one point, horizontal pod autoscaler is no longer supported under this version, but using a new version called autoscaling v1. And in this particular cluster, it still has some old version HPA. And of course, API server cannot recognize it anymore, it cannot find it. So we didn't find the fix for that issue, but still, we don't need to panic. All we need to do is just be a little more creative here. The safe approach would be to delete the existing old version HPA, right? And create a new one with the correct version. Of course, that would come with some downtime. Let me remind you guys again, control plane downtime does not mean cluster downtime. Your pod is still running, your application is fine. But if you really do not want a control plane with downtime, there is manual SCD surgery that you can do. But keep in mind that messing up with the raw data is always dangerous. You better make sure what you're doing have a backup plan. All right. We talked about API server, we talked about controller manager, and even SCD. And I promised some of the guys here that we were going to talk about scheduler, and here we are. I'm actually going to spend a whole section talk about scheduler, which is we should trust scheduler. If anything happens, if a scheduler is unhealthy, instead of thinking that scheduler is wrong, actually look at the scheduler message and see if it can give you the clue, because our scheduler engineer did a really good job. The scheduler is very robust. So I want to start with some very important scheduler concept that would help you interpret scheduler issues. The first one is node selector. It provides a very simple way to constrain pods to nodes with particular labels. For example, you can say that you can ask the scheduler, say, to please schedule this pod on a node that have GPU, right? And then followed by that is the node affinity and node tings. Node affinity is a property of pods that attract them to certain node. And tings is the opposite. It can repair the node from a set of pods. Remember that node that have GPU on it, it can tell the scheduler, only the pod that need the GPU can be running on me. So if you have some scheduler issue, those are the things that you want to check, like if they're set properly. And then there is possible core down nodes. When a node is core down, it's unschedulable. It's definitely going to impact your scheduling. And then there are other things like unavailable nodes for whatever reason. there are insufficient resources. For example, you want to schedule 5 million pods on 3 small nodes. That's not going to work. With all this concept, instead of talking about one real issue, I want to give a summary of how to interpret unschedulable. So the symptom could varies from sanity check tells you that scheduler is not working, to scheduler use up too much resource, too many pending pods, or no pods get scheduled. And then there are some analysis tools you can use. For example, scheduler metrics. There are a lot of useful information in there. I know they added a lot of new useful metrics lately. Then you can also check the scheduling related events for specific pods that you care about and see if everything looks fine. And then you can always check scheduler log as well. And the root cause could be from any of the things that we've just talked about. And last one, this is a message that I want to deliver. I just want to repeat it again. If the scheduler reports your pod as unschedulable, it's usually right, and will try its best to tell you why not. The trick is to listen to it and use that as a clue to find out why your control plane is acting funky. And there is a very good talk given by Marek Grabowski, his our colleague. He is a real control plane expert. He has a talk from last year's KubeCon on the scheduling features. You can check online. And with all these nice tricks that Joe and I just talked about, let's go back to the very beginning. 不忘初心。我们为什么要来这个 talk? Why do we need to come to this talk? Because we want to keep our control plane healthy, right? What if we do not need to use any of the trick at all, and we have a healthy control plane to run all the time? So what are the puzzle pieces that we could put together beforehand to have a healthy control plane running? We won't have time to talk about each in detail, but I'll at least give you some basic resource you can check after this. Security is definitely play a big part in this picture, and you can check this talk about Kubernetes for enterprise security requirements. It's given in the Google Cloud Next conference. And the next one, as I mentioned in one of the example, an accountable monitoring alerting system is very important. There are a lot of nice products outside that you can find one that fits your needs, or you can read this Kubernetes official documentation and build your own. Resource quota, some people talk about resource quota before this talk. So there is a series of video called Kubernetes Best Practice. One of it is to teach you how to set resource requests and limits in Kubernetes. And then for scalability, you do want to have a proper size of master and cluster, or your nodes. And in the Kubernetes official documentation, there are some informations about that. And then, last but not least, upgrading and backup is important. You hear me mention a couple of times in our talk, upgrading. And the good news is the best resource is here in this KubeCon. Tomorrow at 11:30, our colleague Chao is going to give a talk. Here he is. Say hi to everybody. So it's purely about safely upgrading Kubernetes cluster. Chao is one of the earliest developer in Kubernetes. He's a ping pong lover. We have a ping pong table downstairs. And I've seen the slides, very informative. I learned a lot. I hope you will too. And that's question time. Yes.
I have a question. We always find some problem by the condition and the event on the KBS object, but sometimes some core components errors hide in the log, not in events or conditions. So it's very hard to find the relationship between the conditions and the component. I think maybe we should define a different kind of event, such as cluster or component, to attach the errors in the core component to the specific event. What's your opinion about this?
Still processing, but I think it's worth talking about. I think one of the reasons why we give presentations like this is because we want the shelf life of them to be short. I would like this presentation to become obsolete because we make Kubernetes better. So yeah, I would love to talk about things like that. I think what you've mentioned sounds like a gap to me, something we could improve. Other questions?
So I think you guys might have a lot of experiences with maintaining an operation for very large clusters and also very complex systems. So what is the best practice when you have very tricky problems and you don't know where to look at? Maybe it's a network or it's infrastructure or anything within the cluster. So any best practice for that part, including monitoring and alerting?
Yes. Do you want to try that one, Wenjia? Or should I give it a shot? Yeah, I think you already mentioned it there. I think monitoring is your first line of defense, and you should use that to try and guide you into diagnosing the issue as far as you can. One piece of feedback I might give to people is if you run into an issue where you end up spending a lot of time just trying to find that first breadcrumb, spend some time afterwards thinking about why that was, what monitoring was missing, what infrastructure was missing to trace that problem. Basically do kind of a postmortem on that issue and use that to improve your monitoring and your first stage of identifying an issue and tracing it so that next time you're in better shape.
Yeah, one thing I want to add is that you can see there are so many different enterprises using it, and the people from startup all the way to the big company like Google, we even have internal use cases for Kubernetes. So the use cases are so different that it's really hard to find a standard to like how to use Kubernetes in a certain way. But one thing that is that you can definitely find other people who use it the same, probably similar way as you are. And if you post questions on the Kubernetes GitHub or Stack Overflow, you're probably going to find some answers. And during the issue discussion, you're probably going to find the fix, and you can contribute to the community.
Thank you. My question is that the most of issues currently we have when we have a HA control plane and a lot of the nodes is etcd related. So do you have any suggestions about how we can diagnose etcd related issues?
I'm going to give a talk about this at KubeCon Seattle, so watch the slides when we present those. I think a lot about high availability etcd. There are certain minimum sane versions that I've talked to the community about before, and I'm trying to think at the high level what I can tell you. It's a detailed topic. Maybe we'll save that for the Seattle conference.
Okay.
Thank you, everyone.